So good afternoon, everyone. Welcome to the NITheCS, the Monday afternoon NITheCS colloquium. My name is Francesco Petruccione, and I'm at the moment the interim director of NITheCS. It is a real pleasure this afternoon to introduce to you Dr. Eric Maluta as our speaker. Eric was born in the Mutale region of Limpopo, and he did his undergraduate studies and his honors degree at the University of Limpopo, after which he moved to the University of Venda, where he did his master's in renewable energy. And after that, with a scholarship, he moved to the UK at University of Bath and completed there in record time his PhD on simulation of dye-sensitized solar cells. Yeah? And I guess when he came back to South Africa, he joined the University of Venda. Yeah? And at the university, he's not only active at the University of Venda, he plays also an important role in developing and improving the physical sciences curricula, in particular for rural secondary schools. And he is heavily involved also in the upgrading of the education of our teachers, in the organization of the South African Science Week and many other science and engagement events. Yeah? He's also a member of the Council of the South African Institute of Physics, and he's in charge of the education portfolio there. Yeah? And this afternoon with us, so he will tell us just now what his research is about, so I don't have to mention it at the moment. And with us this afternoon is also Dr. Regina Mapanga. She's a principal researcher and research group leader at the CSIR in the Next Generation Enterprises and Institutions cluster. Regina is also a NITheCS associate, and she's also working on computer modeling of materials, and that's why she kindly offered to help us moderate the questions after and during Eric talks. Yeah. So just before I ask Eric to start with his presentation, please make use of the Q&A facility that you see at the bottom. What is it? At the bottom right? Yeah, sorry, I had to look. Bottom right of your Zoom screen to ask questions, and Regina will give a look and then pose the questions in a coordinated way to Eric after the talk, or if there are urgent questions during the talk. So Eric, please, if you would like to start your presentation, you already shared your initial slide. You are welcome to start. Thank you very much, Eric, and thank you very much, Regina.
Thank you very much, Francesco, for the opportunity, and the NITheCS family for giving me the opportunity to share my work at the University of Venda. As you said, Eric Maluta from the University of Venda, currently in the Department of Physics. I'll be sharing the work we are doing under the topic theoretical study of Brookite TiO2 as a material for dye-sensitized solar cells. And the outline of my talk, I will just introduce the dye-sensitized solar cells, also including why we are really interested on that, and then look at the methodology we are following. Then I will talk about some results which we have done during the past few years also. But this will be the recent results which we have done currently. And then I will summarize my work. And then after that, it's gonna be question and answer. The dye-sensitized solar cell is just a simple solar cells comparing to the other generation of PV, the first, the second, and now coming to the third generation. The dye-sensitized solar cell comes in handy as it's a low cost solar cells. And apart from that, it's absorption, its theoretical absorption efficiency is high compared to the silicon solar cells. but its problem is currently the performance efficiency is very, very low. But the structure of these solar cells is simply made of few materials where we have, if you look at my left-hand side, we have the tin oxide, which is the transparent electrode or the counter electrode. Then we have the yellowish thing, which is the TiO2. And then we have the black things, which are the dye molecules. Then we have the electrolyte, which are iodine triiodide electrolyte. And then we have the counter electrode, where we have the platinum coated glass. Then the issue with these solar cells, the main components for photon absorption are the dye molecules and the semiconductor TiO2, which on my left picture here, it's indicated as yellow. Then the work which we are showcasing just the relation between the dye molecules and the TiO2, which makes more of the efficiency of the dye-sensitized solar cells. On the other picture on my right, here I'm showing the light absorption on the dye-sensitized solar cells, which is simply when the light strikes the solar cells, then the dye molecules, which now here are red, they become excited. And when they are excited, they eject an electrons into the TiO2. After injecting an electron in the TiO2 semiconductor, then the electron moves by diffusion to the transparent electrode and then to the counter electrode, generate the current, while the electrolyte on the other side regenerate the excited dye so that then it can go back to its normal state. But then it means the most important things now is the dye molecules, which are these red dots here, and the TiO2, which is the grayish color here, because whatever is happening with the electrons is just between these two things. But then means then when these electrons are diffusing in the TiO2, we have the effective electron lifetime of the electrons, which also comes in hand, the electron diffusion length also of the electron, and then the electron diffusion coefficients also. Those are the other important players as the property of the electrons diffusing through the TiO2, which then, as I said, then researchers are giving efforts to understand this. And we are also, as the research group at UNIVEN, we're giving effort to understand this relation between the two here. But then apart from the dye molecule itself, we have the TiO2, which we have to cover its surface. And here is an example to say what we believe is if on the TiO2 surface, we have more dye, like the picture on my right here, then it means we will be able to have more electrons being injected into the TiO2 because the dye molecule on the surface will become excited and more electrons will be injected. Then we have high efficiency. But if it's low dye uptake or we have little coverage on the surface of the TiO2, then also the current won't be high, the efficiency will be low also. That's the other problem we have. That's why we are trying also to understand the TiO2 and the dye molecule, just to look at their properties, the absorption property, the light harvesting efficiency of the molecules and the TiO2, and also looking at now we have the sandwich of the two, when we absorb the dye into the TiO2, what's really happening on that surface. But then the TiO2 itself also has its own problem, where we have the high energy band gap of the TiO2, whether it's anodized, rutile, and the Brookite. Probably more research has been done on the anodized and rutile, but currently we're looking at the Brookite because Brookite has high photocatalytic properties, but then its disadvantage, it's difficult to be synthesized, but currently people got to synthesize the high Brookite, purity Brookite, so that will also improve its application on different systems. Like for our system in the dye-sensitized solar cells, then it means the new way of synthesizing Brookite, then that will make researchers and people who are really looking at improving the dye-sensitized efficiency to look at Brookite rather than looking at the anatides and rutiles, which has been studied for a long time. Then what we are really doing, because now we know the problem of the two properties of the dye-sensitized solar cells, the dye molecules and the Brookite itself, because the Brookite has high band gap, and the molecules, we are thinking that when we have more attached the surface, then we'll have the improvement of the efficiency of the dye-sensitized solar cells. But then what we're really using is just doing a computational studies using the density functional theory, which is the first principle method to solve the electronic structures and energetic of any different materials. But currently we're looking at the semiconductor material. And what we're doing, we are just solving the Schrödinger equations, which also give us then exact results when we are looking at that. But as a computational people, that's where we become lazy. We don't really go deep to understand the equation. And that's where we also need the theoreticians to come and work with us to really go deep to its equation and really understand that. But really what we are doing is just to calculate the ground state energy of the material and then look at the different properties after the material is relaxed. And currently the methodology we're really using, it's based on the Material Studio, where we have the custom software which is implemented under the Material Studio, and that's where we are doing our calculations. And what we are doing is just to make an approximation using the general gradient approximation with the Pedderby way, which then these two just describes, sorry for that. These two just describe the correlation between the functions of the material. And what we do then is to look at the convergency of the material, which then gives us the cutoff energy. And then we calculate the K-point sampling, the Brillouin zone K-point sampling, which we perform using the Markov-Peck mesh. And then after making the material to be relaxed, then what we do, we look at the different properties of the materials and then analyze those different properties to see whether what we are looking at on the material is what we are really going to either say we can improve the efficiency of the dye-sensitized solar cells when we compare what we have done with the theoretical calculation done by other people and the experimental calculation done by also other people. And the first thing what we are looking at is just the band gap engineering, where we look at the doping of different elements on the surfaces of the Brookite solar cells. Not Brookite solar cells, but the Brookite surface of the TiO2. But the issue is, because I've said we have chosen the Brookite unit, it's just a unit cell as a 24 atom, where we have 8 titanium and 16 oxygen, because normally we have 1 titanium to 2 oxygen. And then it's just an octahedral where the Ti atom binds to 6 atom, and their energy range is from 1.8 to 2.05 angstrom. And then what we have here, we are showing the calculated properties of the bulk TiO2 Brookite, where what we have, we normally use the literature to look at our current calculated values, whether the experimental literature and the theoretical, the other theoretical calculation and what we get, are they in line with each other? And then when we look at that, then we can continue to look at the other properties after making sure that really our bulk properties after the relaxation of the materials are in line with the other experimental or other literature values. Then this is just the bulk structure, which we dope with other elements. And this is the properties of the bulk structures, where we look at the band gap and the dose, the density of states. And on those, we are just looking at what the oxygen and the TiO2 are contributing to the structure. And for the bulk property here, our band gap, as I said, it's very high. For the calculated year, the band gap value is about 3.42, which when we look at absorption of the TiO2 Brookite, then it means it's absorbing under the ultraviolet, which for the solar cell application is not needed. We need it to absorb from the visible light to the near infrared. And then the dose just shows us the contribution of the oxygen atom and the TiO2 atom before introducing other materials in the system. And what we did was to look at the transitional metal doping. We have doped with different transitional metals, but here I'm just showing the doping by ruthenium and doping by platinum for the different Brookite surfaces. And what we have 1,1,0 surface on my left, and we have the 1,00 surface. Oh no, 1,00 surface is on my right and 1,10 surface on my left. And then we can dope with the different thing, like the B here, we dope with ruthenium, and on the C, we dope with the platinum. And what we are looking at, like what we said there, is just the band gap engineering. We are looking whether we will reduce the band gap or what is happening with the contribution of the Ti atom, the oxygen, and now the new material, because now what we did is just to come up with a foreign element into the surface of the TiO2. And these are the band structure and the dose. Here we have the Pu 101 and 100 surface. This is the right is 100 surface, and on my left is 100 surface, on my right is 110 surface. Then you can see that the surfaces has higher band gap compared to the bulk structures, which that it's also in line with the other literature to say the surface has more higher band gap compared to the bulk structure due to the change in the atomic numbers and atomic structure of the bulk and the surfaces. Because to get the surface, we are cutting the bulk into different surfaces. And then when we do the doping as I said, what we're doing is to include now a foreign element to the bulk, or not to the surfaces, or we are just making it that the surface now, the pure surface become, we put a defect on the pure surface, and putting that defect, what we see compared to the other one, we can see that now we have some contribution of these elements, the doped elements now, because they show the contribution in between here on the band gap. And the other thing is, when we see this contribution here, also the band gap is reduced, which means that now the surfaces can, apart from absorbing in the ultraviolet, they can now absorb on the visible region and towards the near infrared. And this is the optical property where we are just looking at the absorption between the pure surface, where if you look at the two figures on my left and the right one, the 1001, we can see that the pure surface is more higher here, but then it comes down to around 400 nanometer. But when it's doped with ruthenium and platinum, then we are changing its absorption. Then the absorption now goes higher from above 400 and so, which means we were able to increase the absorption of the two surfaces. And this is one of the results we were also looking to achieve, to say, provided this Brookite surface or Brookite bulk structure can absorb to the visible and to the near infrared, then we will be able to extract more of the electrons, due to the fact that the dye molecule we are using is either in organic or inorganic dye molecules. And the current situation, people are looking at organic dye molecule because they are cheaper, they are easy to synthesize. And then it means if the Brookite also, the Brookite surface can also absorb from the near, from the visible to the near infrared, then the organic dye molecule also will be able to inject more of the electrons, which can diffuse more on the Brookite surfaces, because now we have reduced the band gap. And apart from metal doping, we use the non-metal doping, looking again at the different surfaces to see what is happening with the metal, with the non-metal doping and co-doping. And the property we're looking at is still the band gap and also the introduction of the new activities due to the doping. On my left here, where I'm moving the cursor, you can see that the pure structure, the loss of the pure structure shows that there's no any other thing between the band gap. We can just look at the band gap, but then when we dope it with the carbon, then we can see that now, due to the foreign element which has been introduced, then we were able also to have more, some of the activity or the introduction of more bands between the band gap. And now we also reduce the band gap, which is what we wanted to say, to achieve, because then now this means that if we reduce this big band gap and introduce more of the bands here, then our surface or the bulk structure will now be able to be active on the region of the visible region and towards the near infrared. And this we can see from monodoping and also co-doping, as indicated on my right-hand side where I'm moving the cursor, that the band gap is reduced. And when the band gap is reduced, we also have introduced the new bands between either on the valence side or on the conduction side, which that also comes depending on the non-metal we're using or on the metal we're using, whether we are shifting, we are including the bands on the conduction band side or on the valence band side, which is what we see from our results. We also look at the absorption, the optical absorption curve of non-metal doping, and we realize we can see the same similar trend of saying our pure surface absorption is improved to the other side, as I'm moving the cursor here to show that then our absorption is improved, looking at the pure one, which is the black one, which comes and dies around here, the 2-0 surface. But when we do the doping, then we can see that we are improving the absorption even towards the near infrared. And then what we also look at is the dielectric function as it described the polarization and absorption of the material, to see what is really happening on that. And on my left, we did also the monodoping and co-doping. And then we have seen that we also change the dielectric constant of this of the surfaces by including the foreign, or by putting in more of the foreign elements in the system, because we're just including a defect on a pure system. And this also means that looking at these properties, it also gives us a way of thinking that really, if this can be done experimentally, then we will be able to improve the efficiency of the dye-sensitized solar cell. Apart from looking at the surfaces and the bulk structure, we went further and we look on the nanoclusters, where we're building the nanoclusters by using different TI elements. And as is 1:2, then normally we will have on my right here, we have the TI5 Brookite cluster, where we have 5 TI, and the other one is 8 TI Brookite cluster, where we have the 8 TI elements. And the other on my left, below the bulk structure, this is like 68 TI elements. Then it means the oxygen are 2 times the number after the brackets, because it's 1 to 2. And then we try also to understand the properties. And the advantage of the clusters is that we are able to also look at the UVV's absorption to see how the absorption is. And looking at that, we can say for the 2 clusters that at least when we go to the clusters already, they have some absorption just around the 400 nanometers. And our aim also was to look at what is, if we combine this with the dye molecule, how far are we going with the absorption? And these are the contribution which we're looking at on how the oxygen and how the TI elements are contributing towards the band gap and the other properties. And for this other one here is for the TI5 nanocluster. We have the TiO2 8 nanocluster on my right where the CSI is, and then the TiO2 68 nanocluster. Then you can see how the oxygen and the TI elements contribute when we have the clusters. And just there, next to the zero, that's where we have our band gap, like here and there on the other side. And as seen from the other surfaces, when we introduce other foreign element, or when we dope with non-metal or metal, then we are reducing also the band gap of these clusters. But now what we wanted to understand was to look at using these surfaces, clusters, and bulk structure. What will happen when now we have the dye molecules? And what we did was to look at the polyene diphenyline dye to be adsorbed on the Brookite nanoclusters. These are the optimized structures of the different polyene diphenyline dyes, where we have the D5 here, and then we have D7. That's the difference between the two dye molecules. I will also show the chemical structure after, but this is just coming when we are doing the optimization on the using CASTEP and also on the Material Studio. But there are normal chemistry structure is this one, where you can look at the difference between the D5 and D7, which comes with this nitrogen and the other carbons which are added, and those are the what gives difference on the different dye molecules here. And what we are doing, like what I explained, that we're using the CASTEP, the GGA with the PTBWare. And what we're doing is just optimize these molecules, draw them on the system, optimize them, and then understand the HOMO and the LUMO, the highest occupied molecular orbit and the lowest unoccupied molecular orbit of all these dye molecules. And these are the structure after optimization. We can see how the highest molecular orbit for each dye sits and the lowest molecular orbit for each dye sits. But then because these dyes are going to be adsorbed on the TiO2 surfaces, then it means on the combination, then the other one goes to the TI, because now we will have the HOMO on the dye and the LUMO on the TI. Hence, the dye molecule absorb and then inject to the TiO2. But then the properties, what we are looking at now, we look at the absorption spectrum of these different dyes, and then we also calculate, sorry for that, we also calculate their absorption efficiency, light harvesting efficiency, which is calculated by this formula here. And at each highest wavelength, where then from the figure on my left here, where there's a cursor, we can see that each dye molecules, D5, D7, D9, and D11 has its own highest wavelength, which is the H lambda here on the table. Then we can calculate their light harvesting efficiency using that formula there. And from the table, it's clear that the light harvesting efficiency for this type of the polyene diphenylamine dyes are more than 65%, and which these are the natural dye. And that shows that the natural dyes gives us advantage. That will be seen when I'm talking about the inorganic dyes, which is coming, the ruthenium one. But the organic dyes now shows an advantage because now their light harvesting efficiency is high, which is one of the advantages of using the natural, the organic dyes. Then looking at the same, going to metal dye or inorganic dye, or like ruthenium, which was one of the dye which was used from the beginning of invention of these dye solar cells. Then we also did the same, optimize it, and then calculate its properties. We look at its HOMO and LUMO to see where it sits before we absorb it on the TiO2. And then this is the structure just showing the HOMO and the LUMO of the ruthenium dye. This is the simulated UVs, where now we can see also it has different maximum peaks, where we have the lowest here, it goes up like that. But then after getting that, then we can also calculate its light harvesting efficiency. And from the different wavelength, we can see that the light harvesting efficiency of the inorganic dyes is low compared to the other one, which now says that other one has it has advantage. And these are some of the work which has been done compared to what we found here. And we also see that our work is also similar to other work which were done experimentally and computed work. Then what we do is just to look now on adsorbing the dye molecules. On my left here is the top structure here. On the different surface is like we have the dye here and the cluster here, which is the 8-element Ti elements cluster, and the 68 Ti element cluster with the dye molecule on top. And after optimizing the structure, we'll look at the different properties. Then we can see that the HOMO here, it's on the dye, and the LUMO goes to the Ti elements. Even it can be seen here that the HOMO is on the dye and the LUMO is on the Ti element. Like what I was saying, that really we want to have more of occupation on the dye so that there will be more electrons injected to the TiO2 when we are really working on the principle of the solar cells, and that will improve the efficiency of the solar cells. And this shows the same way of for our results to be correct, to say we want more of this, which is we want more occupation on the dye molecule and then few here, so that at least we can inject more to the other side. And this is the absorption now of the two things which I started to say they are the main important properties of the dye-sensitized solar cells. And then we look at the absorption spectrum. And if we look at the TI5, we can see that this is the without any dye, and here is with dye. I think I made a mistake, it must be 8 here, it doesn't have to be 5. And because I'm comparing 8 and 8, then we can see that when we include the dye, we also see the absorption here still improve the absorption from 400 to 600. But theoretically, what we want is just to move from 400 to the near infrared, about 700 there. And the other thing which we can calculate is the absorption energy, just to indicate whether after absorption, our cluster of absorption is stable. And that gives us a way of showing whether we have improved the system which we are looking at, to say we can improve it by looking at the absorption of the dye molecule on the surfaces of the Brookite, whether it's the Brookite bulk structure, the surfaces, or the nanoclusters, or any nanomaterials which we can think of. And just to summarize, to say, when we are doing this analysis of the geometric parameters of the bulk TiO2, the surfaces, and the nanoclusters, we have seen that most of our calculation, they are consistent with the experimental work done and other work done somewhere, which give us also more knowledge to say whatever we are doing, it's still correct compared to the other work. And we can also shift this to the experimental side, getting people who can be working on that, so that now we can see whether this really can improve the efficiency of the dye-sensitized solar cells. The co-doping, whether with a metal or non-metal, also exhibits better results, because we can reduce the band gap. We can see the introduction of new bands, on whether on the valency band or the conduction band, and whether we use the clusters or the surfaces. When we absorb the dye on top of those things, we also see that we improve the absorption towards the near infrared, or from the visible until the near infrared. And most of this improvement is coming because we really want to shift the high band gap absorption of the TiO2 from ultraviolet, just to start from the visible to the near infrared. And that comes in handy when we absorb the dye on top of that. These are some of the references I've used, and I would like to acknowledge and the contribution and collaboration which I have, contributors which are my students. I have Nemziva Durisane, Rutendo Putu, Fortunately Bele, Chipuarangwa, Steve Dima at CSIR, and my collaborator, Regina Mapanga at CSIR. And this work is being done at the University of Venda. The calculations are done from high performance computing. The National Institute of Theoretical Physics also has given us some funding, and they're funding our students to work. And we have NRF Tutuka program, MESITA, and Department of Science and Innovations, which are also helping us with this work. And thank you all.
Yeah, thank you very much, Eric, for sharing your knowledge on materials for solar cells. Thank you very much. I would like now to ask Regina to guide us through the question session. And I think there is, at the moment, there is just one question in the chat by William Horowitz. I don't know if you saw it, Regina. Otherwise, we can. I can quickly offer William to talk and pose his question in person. So, William, if you would like to share your question, and while you ask your questions, the other participants are welcome to formulate their questions as well, or just to raise their hand if they prefer to express the question in person.
Hi, Eric. So this is Will Horowitz. So thank you very much for this very nice talk. So if I understood your presentation, when you've introduced this organic dye to the Brookite, you're able to shift the absorption spectrum to the visible, and that the light harvesting efficiency is greater than 60%. So as a non-expert, that seems really great. My question is, does that mean that this type of a solar panel is now commercially viable? Thank you.
Okay, thanks, Will, for the question. This type of solar cells are commercially available, but currently the problem with them is the lifespan, which we have, because of the organic dye lifespan is not very high. And also, like when I introduced, I have talked about the electrolyte, which also gives this type of solar cells a little bit more of its disadvantage, because they can't really work for a long compared to silicon solar cells, which are around 25 years outdoor.
Okay, thank you.
Yes, Prof. Thank you. Thank you so much, Dr. Maluta, for an insightful talk. There is another question from Q&A section. It is from Adedabo, and it says, how did you determine the position of the dye molecule on the TiO2 surface?
Okay, there are two ways to do that. You either look at on the Material Studio, it gives you a way of looking at the absorption sites. Then you can locate the absorption sites and put the dye position there. But for our work, what we are doing, we are not looking at the absorption site. What we are doing is just put the two things together and optimize it. Then they normally absorb at wherever the position absorption is when we are doing the optimization, which is what we've done on this way. But there's another work which we've done where we use the absorption locator to locate where the dye molecule can be absorbed.
Thank you. Regina, can I ask a question to Eric?
Okay.
Thank you. Eric, sorry, you mentioned...
Yes, please, you are more than welcome.
Yeah, no, thank you very much. Thank you. Eric, you mentioned your calculations at the CHPC. What kind of software tool do you use for this kind of calculations?
Oh, the software tool we're using is Material Studio, where we have it has a built-in several modules inside, but we're using the CASTEP currently. But some of the work which I didn't show, we have used the Gaussian.
Ah, okay, okay.
And yeah, we can also do this with the Quantum Espresso.
Oh, okay, 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 excellent, excellent. And Eric, sorry, I'm a little bit ignorant in this thing. There is also one software package, I think, called Schrödinger. Could that also be used, or does that do some other things?
No, it can be used.
It can also be.
Yeah, that's the new software, and they are making it, it's more simpler compared to the Material Studio we're using.
Okay,
it's more user-friendly.
Okay, okay. Does the CHPC have it as well, the Schrödinger one?
Currently, no. They were trying to look whether they can use that and change from Material Studio to Schrödinger one, but I think most of the researchers were not willing to.
Okay, even if it's more user-friendly. Okay. Okay, yeah, that's the power of habit, I guess. Yeah.
Yeah.
Okay. Yes, maybe just to say something in line with what Prof. Petrosian has just said. Sometimes it's not about user-friendly, it's about the familiarity. When people are used to something, it's not easy to change to a new one. But we've got another question there under our Q&A section. It's from Camille. The person is asking, is there any relation between the mechanism of solar panel and photosynthesis in plants?
Yeah, the dye-sensitized solar cells is mimicking the photosynthesis in plants. That's why really the dyes comes in to play the role of photosynthesis as absorbing the lights and then injecting it to the TiO2. Normally, these dye molecules, the organic dye molecules are really coming from the chlorophylls of some of the plants, and we are really mimicking the photosynthesis.
Interesting. Okay, interesting. Yeah, Eric, it doesn't seem, unless Regina sees something that I don't see, it doesn't look like we have any more questions. So I would like to thank, first of all, Eric very much for a very interesting talk. And I would also like to thank Regina for being with us this afternoon and moderating the questions. And I hope that very soon Regina will be also swap role with Eric so that she will present her results, and maybe we can ask Eric to moderate the question on that occasion. Yeah. So thank you very much to everyone. We are looking forward to see you again all next Monday. You should get the announcement of the talk on Monday, latest tomorrow morning. Yeah. So thank you very much, Eric. Thank you very much, Regina. Thank you very much to all the participants, and please keep staying safe. Yeah. And all the best. Thank you very much.
Thanks.
Thank you. Bye.
Thank you. Bye-bye.